In a universe teeming with mysteries, few questions stir the human imagination quite like the idea of calling Mars home. Picture a future not just visited by spacefarers, but bustling with thriving Martian communities. As we gaze at the red planet glittering in our night sky, the notion of terraforming it to convert its barren landscapes into lush, Earth-like environments stirs both wonder and skepticism. Could it be within our reach to turn Mars into a place where life not only survives but flourishes? Today, we'll unravel the intricate tapestry of science and ambition that underpins this vision. From unlocking the secrets of Mars' icy poles to harnessing advanced technologies yet to be imagined, we'll venture into a future where interplanetary living might just be a part of humanity's next chapter. So, join us as we delve into the possibilities and pitfalls of this extraordinary journey, setting the stage for a captivating exploration of our potential Martian future. Imagine stepping onto the Martian soil and seeing vast stretches of green fields, rivers flowing under a blue sky, and a breathable atmosphere, an Earth away from Earth. This is the bold vision of terraforming Mars, a concept that has tantalized scientists, writers, and dreamers for decades. The seeds of this idea were sown by luminaries like Carl Sagan, who envisioned life thriving beyond our planet's confines. Sagan was not just a scientist but a storyteller who inspired generations to look up at the stars and see possibilities rather than impossibilities. The allure of terraforming Mars emerges from a blend of practical and fantastical perspectives. Scientifically, Mars is intriguing because of its similarities to Earth. It has seasons, polar ice caps, and day-night cycles comparable to our own. These features mark Mars as the most viable candidate within our solar system for terraforming. But practicalities aside, there's something deeply compelling about Mars that captures our imagination. Historically, Mars has been the focus of countless works of fiction and speculation. From H.G. Wells's The War of the Worlds to Ray Bradbury's The Martian Chronicles, Mars has been seen as both a mysterious adversary and a canvas for human dreams. It represents a frontier, the new Wild West for the 21st century, where humanity's pioneering spirit could unfold in unprecedented ways. The modern vision for terraforming Mars involves transforming its atmosphere and climate to enable sustainable human life. This would mean warming the planet, thickening the atmosphere, and introducing water and life forms. The task is monumental, akin to playing cosmic gardener on a planetary scale. But why undertake such a colossal project? The answer lies in a mix of survival and aspiration. As our own planet faces environmental challenges, looking to another world offers a long-term insurance policy for humanity's future. Moreover, the process of terraforming itself pushes the boundaries of human innovation and engineering. It would require advancements in nanotechnology, bioengineering, and climate science, catalyzing technological growth that could have transformative benefits here on Earth. At the heart of this ambition is a desire to transcend our planetary limitations. For many, Mars represents hope, a symbol of new beginnings and the eternal quest for knowledge. It's a testament to human curiosity and the desire to explore, to reach out into the cosmos and stake a claim in the vast unknown. This dream unites us, igniting scientific passion and capturing our collective psyche with its audacity and scope. Visionaries today, from Elon Musk with his plans for Mars colonization to NASA's ongoing exploration missions, carry the torch of this ambition, fueled by the same dreams that were planted by past thinkers. They remind us that what was once science fiction is inching ever closer to becoming science fact. As we stand at the brink of this potential new era, we find ourselves asking, what kind of stewards will we be on a new world? How will terraforming Mars redefine our place in the universe, and what will it teach us about safeguarding our own planet? As we speculate on these questions, one thing remains clear. The journey toward making Mars habitable is not just about transforming a distant planet, but also about redefining humanity's role in the cosmos. It's about imagining a future where life thrives, unfettered by the constraints of its earthly origins, and embarks on a new chapter among the stars. Mars, the fourth rock from the Sun and our cosmic neighbor, is a planet of paradoxes. Its ruddy hue, carved by eons of cosmic forces, hides the secrets of an alien world vastly different from our own. To comprehend the enormity of the task of terraforming Mars, we must first understand the environment we are dealing with. Mars is a world of extremes where giant volcanoes like Olympus Mons dwarf those on Earth, and expansive plains like the Hellas Basin stretch as far as the eye can see. Despite these awe-inspiring features, Mars presents a harsh reality, a landscape as unforgiving as it is magnificent. Let's start with Mars' atmosphere, or rather, its lack thereof. The Martian atmosphere is a thin veil composed mainly of carbon dioxide with traces of nitrogen and argon. At just about 1/100th the thickness of Earth's atmosphere, it offers little protection from cosmic radiation and does a poor job of holding in heat. As a result, surface temperatures plummet to -60 degrees Celsius on average, making it bitterly cold. These frigid conditions, coupled with the low atmospheric pressure, mean that liquid water cannot exist on the surface for long. Instead, water is locked away in polar ice caps or trapped beneath the surface in permafrost layers. Scientific missions have greatly enhanced our understanding of Mars. The Viking landers of the 1970s were pioneers, sending back the first images and data from the Martian surface. They provided invaluable insights into the soil composition and atmosphere. More recently, the Curiosity rover has been conducting detailed analyses of Martian rocks and soil, uncovering evidence that suggests Mars might once have hosted conditions suitable for life. This tantalizing data revives the hope that Mars could be made habitable again. However, the obstacles are formidable. The lack of a strong magnetic field leaves Mars exposed to solar winds that strip away its atmosphere, perpetuating its barrenness. The low gravity, about 38% of Earth's, poses additional challenges for how we might build and sustain a new atmosphere. These inhospitable conditions fuel the critical questions scientists must address before terraforming can commence. How do we create a thick, protective atmosphere? How do we warm the planet to allow liquid water to flow? And how do we make Mars a place where life can thrive? Understanding these conditions deeply influences our strategies for terraforming. One proposed approach is to release greenhouse gases into the atmosphere to increase temperature and pressure. This could be achieved by sublimating the polar ice caps or introducing engineered microbes designed to produce oxygen as a byproduct. Another idea is solar mirrors, positioned in orbit to reflect sunlight onto the Martian surface, incrementally warming the planet. Each strategy presents its own set of complexities and technical hurdles, but they all center around fundamentally altering Mars' hostile environment into one more nurturing. The scientific endeavors from missions like Viking and Curiosity have not only expanded our knowledge but also provided a foundation upon which future terraforming efforts might be built. They remind us that while Mars may currently be hostile to life as we know it, the dream of transformation is not beyond reach. As we continue to probe these environmental challenges, we edge closer to the day when the idea of a habitable Mars might shift from the realm of science fiction to that of scientific reality, driven by innovation and a relentless human spirit. The journey to Mars is as much about understanding a distant world as it is about understanding our own capacities to adapt and thrive in the cosmos. Transforming Mars from a barren wasteland into a lush haven teeming with life is no small feat. At the heart of this monumental task lies cutting-edge technology innovations that could alter the very fabric of the Red Planet's environment. Let's explore the frontier of ideas and inventions that promise to pave the pathway to a habitable Mars. One fundamental challenge of terraforming Mars is atmospheric thickening. The Martian atmosphere, composed chiefly of carbon dioxide, is extremely thin, making it vital to amplify its density to create Earth-like conditions. One promising technology in this endeavor is the production and release of greenhouse gases. Similar to how these gases increase Earth's temperature by trapping heat, strategically introducing them on Mars could warm the planet, melting polar ice caps and releasing more carbon dioxide to thicken the atmosphere. Scientists are currently researching how engineered aerosols and synthetic gases like perfluorocarbons could serve as efficient greenhouse agents on Mars. Emerging research in synthetic biology is also making significant strides toward realizing this vision. Synthetic biology involves redesigning organisms for specific purposes, an approach that could revolutionize terraforming. Imagine bioengineered microorganisms capable of surviving on Mars, engineered to produce oxygen through photosynthesis. These microbes could gradually alter the atmosphere, making it more breathable. Initiatives like the genetic code expansion are pioneering techniques to modify the DNA of microorganisms, enabling them to thrive in Martian conditions. This area of study not only holds promise for Mars but also offers profound implications for biotechnological advances here on Earth. Geoengineering, another critical domain, involves large-scale interventions in the planet's climate and environment. For Mars, this could mean deploying space-based mirrors to reflect sunlight onto its surface, warming the planet and triggering chemical reactions that release trapped gases. Projects are underway to explore how these solar reflectors can be efficiently manufactured and deployed, potentially using materials found on Mars itself. Such technology not only highlights our potential to reshape planetary ecosystems, but also pushes the boundaries of how we conceptualize mechanical infrastructure in space. At the intersection of these technologies lies the concept of in situ resource utilization, or using local resources to support human colonies and terraforming efforts. Mars is rich in raw materials such as regolith and ice, which could be used in situ to construct habitats, generate fuel, and produce life-sustaining chemicals. Advanced robotics and autonomous systems are being developed to mine, process, and utilize these resources, offering a sustainable approach to building a Martian society. However, these technologies are not without challenges. They require rigorous testing and ethical considerations before deployment. The potential ecological impact on Mars's current landscape and the technical hurdles of operating remotely on another planet pose significant questions that researchers continue to address. The journey toward a habitable Mars is as much about innovation as it is about vision. Technological advancements in atmospheric engineering, synthetic biology, and resource utilization paint a future where Mars could be transformed into a thriving world. These developments not only bridge the gap between current capabilities and future possibilities, but also inspire us to rethink our relationship with technology and the cosmos. As we stand at the brink of interplanetary exploration, these technologies are our tools and companions, guiding us toward the dream of a second Earth. They embody the spirit of human ingenuity and remind us that through science and collaboration, the possibilities are as infinite as the stars themselves. Let us continue to dream, innovate, and explore, for the story of Mars is a reflection of our own journey, an odyssey into the heart of what it means to be human. To breathe new life into Mars, scientists are exploring various ways to warm the planet and awaken its potential for habitability. One of the most promising avenues is the strategic use of greenhouse gases. On Earth, we've seen how these gases can trap heat, contributing to global warming. While harmful here, this effect could be harnessed for a positive outcome on Mars. The concept revolves around using greenhouse gases to thicken Mars' thin atmosphere, increasing surface temperatures and potentially allowing water to flow. At the center of this approach is the understanding of how greenhouse gases function. On Earth, gases like carbon dioxide and methane trap heat from the sun, preventing it from escaping back into space. This natural greenhouse effect is what keeps our planet warm enough to sustain life. Similarly, introducing greenhouse gases on Mars could initiate a warming cycle, starting a chain reaction that thickens the atmosphere and raises temperatures. Scientists propose using gases such as perfluorocarbons, which are potent greenhouse gases, far more effective than carbon dioxide. These gases could be manufactured and released into the Martian atmosphere, creating an insulating layer that traps heat. By concentrating them in strategic locations, particularly around the polar ice caps, researchers hope to trigger the sublimation of frozen carbon dioxide and water, releasing these elements into the atmosphere and further enhancing the greenhouse effect. However, this approach is not without its challenges. The vast quantities of greenhouse gases needed to significantly influence Mars' climate present a logistical and technological hurdle. Manufacturing and deploying such gases on Mars would require advanced machinery and infrastructure, possibly involving robotic systems capable of operating in the planet's harsh conditions. Moreover, the ethical and ecological implications of altering an entire planet's climate must be carefully considered to avoid unintended consequences. The lessons from Earth's climate challenges offer valuable insights into this ambitious endeavor. Our understanding of climate change on Earth, how greenhouse gases have led to global warming, and the subsequent effects on ecosystems provides a cautionary tale. It teaches us the importance of monitoring, regulating, and predicting the impacts of climate intervention. These insights are critical as we consider deliberate climate modification on Mars. Ensuring that we can carefully control and reverse any adverse effects is pivotal to this mission's success. The potential for greenhouse gases to transform Mars lies not just in technical feasibility, but also in the broader implications for planetary science and our future as an interplanetary species. If successful, it would demonstrate our ability to reshape celestial bodies, offering a blueprint for future terraforming efforts elsewhere in the solar system. By understanding and controlling greenhouse gas usage, we not only push the boundaries of what is possible on Mars, but also gain tools and knowledge that could help address climate issues on Earth. In essence, the use of greenhouse gases to warm Mars isn't just about altering a distant planet. It's about learning to responsibly manage our impact on planetary environments, whether earthly or Martian. This endeavor could mark a new chapter in how we interact with our cosmic neighborhood, moving from exploration to empowerment and from observation to transformation. As we continue to develop technologies and strategies to achieve this, the dream of a habitable Mars edges closer to reality, offering hope and inspiration for the generations to come. Water, often hailed as the elixir of life, is a fundamental building block for sustaining ecosystems across our planet. Its significance extends far beyond quenching thirst. It plays a vital role in climate regulation, agriculture, and industry. For Mars to become habitable, securing a sustainable water supply is paramount. As we delve into the prospects of Martian terraforming, the question arises: how do we acquire and utilize water on a planet where it doesn't readily flow on the surface? Mars presents a peculiar challenge. While extensive networks of ancient riverbeds hint at a wetter past today, what water exists on Mars is primarily locked away in the polar ice caps or hidden beneath the surface in permafrost. These ice caps are a promising resource consisting of water and carbon dioxide ice. Mining the polar caps represents one viable method for extracting water, but the process is fraught with technological and logistical hurdles. Extracting water from the ice caps would require advanced drilling equipment capable of operating in extreme conditions. This machinery must withstand frigid temperatures, dust storms, and the planet's low atmospheric pressure. Additionally, transportation of extracted water to human colonies would necessitate efficient pipelines or storage systems, raising questions about energy consumption and material durability. Another intriguing concept is redirecting water-rich asteroids or comets towards Mars. This method, though ambitious, offers a tantalizing glimpse into the possibilities of planetary engineering. Many asteroids contain significant amounts of water bound in hydrated minerals. By nudging these celestial bodies onto collision courses with Mars, we could deliver vast quantities of water directly to the planet's surface. However, this approach presents substantial risks and challenges, not least of which is the precise calculation required to ensure a collision does not inadvertently cause catastrophic damage. Terraforming Mars with a reliable water supply also demands attention to the sustainability of the resource. Unlike Earth, Mars lacks a natural hydrological cycle that continuously replenishes water supplies. Therefore, any extraction must be balanced with efforts to recycle and conserve water, using closed-loop systems and advanced filtration technologies. Developing bioregenerative life support systems that mimic Earth's water cycle could prove crucial, employing plants and microorganisms to purify and recycle water within habitats. Moreover, the introduction of water to the Martian environment would likely initiate chemical and geological changes. Liquid water could interact with the surface to release nutrients and support the growth of life forms, such as engineered microorganisms mentioned earlier. This would be a vital step towards creating a self-sustaining biosphere. However, careful monitoring and management would be necessary to prevent harmful interactions or unintended ecological impacts. Addressing these challenges poses not only scientific and engineering obstacles but also ethical considerations. How do we balance human needs with the potential impacts on an alien world? As stewards of our endeavor, our responsibility extends to ensuring that our methods align with sustainable practices and respect for the Martian environment. Ultimately, mastering the art of water acquisition and management on Mars holds profound implications. Successfully navigating these challenges could set a precedent for resource utilization on other planetary bodies, expanding our capacity for interplanetary living. It represents a leap forward in our ability to engineer environments that support life beyond Earth, drawing us closer to a future where humanity thrives on multiple worlds. As researchers and engineers push the boundaries of what's possible, the promise of water on Mars fuels our imagination and determination to transform science fiction into reality. Biology, often seen as the essence of life on Earth, may become a cornerstone in our quest to terraform Mars. The harsh environment of the red planet, characterized by its barren soil, thin atmosphere, and exposure to cosmic radiation, poses substantial challenges. Yet, through the lens of cutting-edge biological sciences, specifically synthetic biology and genetic engineering, we see a promising approach to overcoming these obstacles. Synthetic biology involves designing and constructing new biological parts, devices, and systems that do not exist in the natural world. On Mars, this could mean creating life forms specifically tailored to thrive in Martian conditions. Imagine microorganisms engineered to survive on Mars' surface, capable of performing photosynthesis to produce oxygen, a crucial step in building a breathable atmosphere. These organisms could live in bioreactors on the Martian surface, using sunlight and carbon dioxide, the primary component of Mars' atmosphere, to generate oxygen and organic matter, key building blocks for a burgeoning ecosystem. Genetically modified organisms (GMOS) offer another exciting avenue. By altering the genetic makeup of Earth-based organisms, scientists can introduce traits that enhance their survival chances on Mars. For example, extremophiles organisms that naturally thrive in Earth's most brutal environments, such as deep-sea hydrothermal vents or Antarctic ice sheets, can serve as templates. Their robust adaptations, like resistance to radiation or extreme temperatures, can be incorporated into other organisms to arm them against Martian challenges. These engineered organisms could contribute significantly to terraforming Mars. Beyond producing oxygen, they could help enrich Martian soil, making it more conducive to plant growth. Plants themselves, potentially genetically modified to withstand low temperatures and high radiation levels, could be introduced later to further oxygenate the atmosphere and support a burgeoning Martian biosphere. This process, while gradual, could transform Mars' sterile surface into a lush environment capable of sustaining higher life forms. However, this biological intervention is not without its ethical considerations. Introducing life to Mars raises profound questions about planetary protection and the preservation of potential indigenous Martian life forms, should they exist. There's a moral obligation to ensure that our quest to make Mars habitable does not erase or irreparably alter its pristine environment. Discussions around terraforming often involve balancing human needs with respect for extraterrestrial ecosystems, a dialogue that must continue as technology advances. Furthermore, the deployment of synthetic organisms comes with inherent risks. These include the possibility of unintended ecological consequences or engineered organisms evolving in unforeseen ways. As scientists design these biological tools, stringent containment and monitoring protocols will be essential to mitigate risks and ensure that these life forms remain beneficial. Biology's role in Mars terraforming is a testament to human ingenuity and adaptability. By leveraging the power of life sciences, we not only open up new possibilities for transforming an alien world, but also gain insights into our own planet's ecosystems and resilience. The intersection of biology and space exploration promises not only to extend the boundaries of life beyond Earth, but also to refine our understanding of life's potential and evolution. As we stand on the brink of a biological revolution in space exploration, this endeavor underscores our responsibility as stewards of life. Whether on Earth or Mars, our actions should reflect a commitment to sustainability and ethical integrity, ensuring that our dreams of interplanetary living enhance rather than diminish the wonders of the cosmos. Terraforming Mars is more than a scientific and engineering challenge. It also poses deep ethical and environmental questions that demand our careful consideration. As we envision transforming the red planet into a habitat suitable for human life, we must reflect on the moral implications of such an undertaking and the responsibility we bear in potentially altering an entire world. The process of terraforming could fundamentally reshape Mars, not only physically but also in terms of its inherent nature and any life forms it might currently harbor. Firstly, let's consider the potential impact on native Martian life, if it exists. Mars has long captivated scientists as a potential cradle for life, primarily due to its past conditions that might have been conducive to microbial existence. Ongoing exploration missions, like those conducted by the Perseverance rover, continue to search for signs of ancient life. If life is discovered, even in its simplest form, it would profoundly influence our ethical standpoint. Introducing Earth-based organisms to Mars could threaten or even annihilate native Martian life forms, disrupting what could be the only other example of life in our solar system. Hence, the decision to terraform must be preceded by comprehensive studies to ascertain the presence of life, ensuring that we do not unwittingly eradicate it. In addition to considerations about native life, we must also weigh the moral implications of transforming Mars' environment. Some argue that planets have intrinsic value, suggesting that they should remain untamed and unharmed. Terraforming would irreversibly change Mars' landscape and atmosphere, raising questions about the right of humans to alter other celestial bodies. It challenges us to think about our role as cosmic custodians, tasked with preserving the natural state of worlds beyond our own, while also fulfilling our ambitions to expand human presence in the cosmos. Moreover, it's crucial to balance our technological ambitions with environmental stewardship. The introduction of Earth-based life forms and the manipulation of Mars' climate might lead to unforeseen ecological consequences. Unchecked, such changes could create imbalances or even catastrophic scenarios if Mars were to evolve in unexpected ways. As we push the boundaries of planetary engineering, the need for rigorous monitoring and adaptability becomes evident, ensuring that our interventions are both sustainable and reversible if necessary. Another layer of ethical complexity arises from the potential for economic exploitation. The resources required to terraform Mars are immense, and the process itself could turn Mars into a new frontier for commercial interests. This possibility raises questions about who should control Mars and its resources, and whether profits and power dynamics should influence our extraterrestrial activities. Governance plays a crucial role here, demanding international cooperation and agreements that prioritize ethical and environmental considerations over monetary gains. The concept of planetary protection echoes through these discussions, a principle that emphasizes preserving the innate conditions of celestial bodies and preventing biocontamination. This ethos not only safeguards potential Martian ecosystems, but also protects scientific integrity, crucial for future astrobiological studies. In navigating these ethical waters, we are reminded of our obligation to act with humility and foresight. As tempting as the prospect of a habitable Mars may be, the decisions we make today could echo across millennia. Our legacy in space should reflect a commitment to stewardship and respect for the universe's diversity, ensuring that our reach does not outpace our wisdom. Ultimately, the ethical dilemmas of terraforming Mars compel us to examine the broader question of humanity's role in the cosmos. They remind us to balance ambition with caution, exploration with preservation, and dreams with responsibility. As we stand on the precipice of a new era in space exploration, let us strive to be guardians of both planets and possibilities, ever mindful of the significant responsibility that comes with the power to transform worlds. While the vision of terraforming Mars captures the imagination with its promise of new beginnings, the economic and logistical realities present formidable challenges that must be addressed. Turning Mars into a habitable world involves intricate planning, substantial resource allocation, and staggering financial commitments, raising the question, what is the true cost of making Mars habitable, and who will shoulder this burden? First, let's examine the financial implications. The cost of a project of this scale is almost unimaginable, potentially running into the hundreds of billions, if not trillions, of dollars over several decades. This massive investment would encompass research and development of terraforming technologies, construction and maintenance of necessary infrastructure, and long-term support systems for human settlers. The initial stages alone, launching missions, transporting materials, and establishing basic outposts, would require enormous financial backing. To make this financially feasible, a multifaceted economic model would be essential. Public and private partnerships stand at the forefront of potential funding solutions. Governments like those of the United States, China, and members of the European Union, through agencies such as NASA and the European Space Agency, have historically funded space exploration and could continue to play a crucial role. However, their budgets are often restricted by political and economic considerations at home, necessitating additional sources of funding. Enter the private sector. Companies like SpaceX, led by Elon Musk, have already invested heavily in Mars exploration with plans for future colonization. The commercial potential of Mars, from mining rare minerals to developing tourism industries, could entice private investors looking for long-term returns. This includes tech giants and new space firms, which might exploit advanced technologies developed for terraforming to drive down costs or develop new revenue streams. The economic law of untapped resources and the prestige of pioneering a new frontier could inspire significant capital investments. Economic models could also include innovative financing strategies, such as international bonds or public-private investment funds designed specifically for off-world colonization. Crowdsourcing through global campaigns might also garner support from the public, capitalizing on the widespread enthusiasm for space exploration. Moreover, future Martian settlers might partake in these financial ventures, contributing economically to the development of their new home. Logistically, the challenges multiply. Transporting materials from Earth to Mars is a colossal undertaking due to the vast distance averaging around 55 million kilometers and the immense energy required. Current technology allows for limited cargo capacity on rockets, necessitating multiple trips and increasing costs exponentially. To address these issues, advancements in propulsion technology are critical. Innovations like nuclear thermal propulsion or ion drives could drastically reduce travel time and cost, making regular missions more feasible. Additionally, the use of in situ resource utilization, harnessing materials found on Mars itself, could alleviate some of the logistical burdens. By manufacturing construction materials, fuel, and even food on Mars, the dependency on Earth-based supplies could be minimized, significantly cutting down the frequency and cost of resupply missions. This approach not only reduces logistical strain, but also supports long-term sustainability for Martian colonies. International collaboration would be vital to share the financial, technological, and logistical burdens of this monumental project. A global coalition, drawing on the strengths and resources of multiple countries and organizations, could pool expertise and distribute costs more evenly. Such partnerships would ensure that the monumental task of terraforming Mars is not borne by a single entity, but rather a collective effort that shares the risks and rewards. Ultimately, the economic and logistical challenges of making Mars habitable are as daunting as they are exciting. They require a paradigm shift in how we dream, invest, and collaborate on a global scale. As we dissect the economic landscape of building a new world, it becomes clear that the endeavor is not merely about financial investment, but about pioneering a new chapter in human history. In meeting these challenges together, humanity may find itself not just creating a habitable Mars, but also crafting a more connected and visionary Earth. As we peer into the future, the landscape of terraforming technology for Mars reveals itself as a tapestry of innovation, collaboration, and ambition. Just as the exploration of space has evolved from a solo endeavor into a cooperative venture among nations and private enterprises, so too will the journey to transform the Red Planet into a lively, habitable world. But what lies ahead on this path of technological advancement and cosmic discovery? One promising direction for the future of terraforming involves the development of autonomous systems and artificial intelligence. Imagine fleets of robotic explorers sent ahead to Mars, equipped with the latest AI technologies. These robots would not only scout and map the terrain, but also begin the initial stages of construction and resource gathering. Advanced AI could optimize processes, handle unexpected challenges like dust storms, and operate continuously, accelerating the groundwork for human arrival. In the realm of material science, breakthroughs may produce ultra-light, highly durable materials capable of withstanding Mars' extreme conditions. These innovations would revolutionize habitat construction, making it more efficient and adaptable. Buildings could be 3D printed using Martian soil, exponentially reducing the need for Earth-based supplies. Such advancements would allow us to create structures that can provide shelter, store resources, and even support plant life. Looking at energy solutions, harnessing solar power will likely play a pivotal role. While solar energy is less abundant on Mars compared to Earth due to its greater distance from the Sun, technology is rapidly evolving. Advances in photovoltaic efficiency and battery storage will ensure a reliable energy supply, powering everything from life support systems to industrial machines necessary for terraforming. Moreover, the role of biotechnology cannot be overstated. As we refine our understanding of genetic engineering, the potential to design organisms that can thrive in Martian conditions becomes increasingly plausible. These organisms could tackle the task of slowly oxygenating the Martian atmosphere, break down inert soil to release nutrients, and pave the way for more complex ecosystems. In the not-so-distant future, these biosystems could transform Martian soil to support agriculture, a crucial step for sustainable human settlement. The timeline for these innovations is difficult to pin down precisely, but experts suggest that significant milestones could be achieved within the next few decades. Initial human settlements may be established as early as the 2040s, with larger, more complex colonies developing as we move deeper into the 21st century. A fully terraformed Mars, one that sustains robust life and diverse ecosystems, might be a reality for the generations of the 22nd century. Private companies will undoubtedly drive much of this progress. Enterprises like SpaceX, with its vision of multi-planetary habitation, are already laying the groundwork for Mars colonization. Their involvement accelerates the pace of technological development and introduces competitive innovation. Meanwhile, international partnerships will be essential, pooling global resources and expertise to tackle the immense challenges ahead. Collaborative projects, much like the International Space Station, could foster shared knowledge and distribute costs. In imagining what a terraformed Mars might look like, we can let our minds wander over verdant landscapes interspersed with bustling human settlements. Picture futuristic cities powered by clean energy, seamlessly integrated with ecosystems that include Earth-native and Mars-adapted species. Such a Mars would not just be a refuge for humanity, but a thriving part of an interplanetary community that demonstrates our ingenuity and unity. The future of terraforming holds boundless possibilities, but it also reflects our broader journey as a species. It challenges us to rethink our relationship with technology, space, and ultimately each other. As we look ahead, we embark on not just a voyage to Mars, but a voyage into a future where our dreams of life beyond Earth fuel our innovations and inspire generations to come. As we wrap up our exploration of the incredible journey from envisioning a habitable Mars to grappling with the intricate web of scientific, ethical, and economic challenges, it's clear that terraforming the red planet is not merely an exercise in science fiction. Instead, it's a testament to human ingenuity, curiosity, and our unyielding desire to explore the cosmos. By examining each facet of this ambitious quest, how technology might transform the Martian landscape, the ethical dilemmas of altering alien worlds, and the economic frameworks required to support such endeavors, we uncover insights not only about Mars but also about our own place in the universe. The endeavor to terraform Mars represents a pivotal moment in our evolution into a multi-planetary species. Mars is more than just a destination. It is a proving ground where humanity can test the limits of its technology, ethics, and cooperation. As we stand on the brink of becoming inhabitants of two worlds, Mars serves as a symbol of hope and resilience. It challenges us to push beyond our earthly boundaries, asking what we are capable of achieving together and how we can responsibly expand our horizons. In contemplating Mars' role in our cosmic journey, we are reminded of the lessons it offers. It teaches us about the fragility of ecosystems and the importance of sustainable practices, both on Earth and in space. The challenges of Mars compel us to refine our technologies in ways that echo back to benefit our home planet, encouraging innovation in energy, materials, and biology. Moreover, the ethical discussions surrounding Mars prompt us to reflect on stewardship, urging us to approach space exploration with a sense of responsibility and reverence for the unknown. As we continue to dream of what might be possible, it is essential to engage in meaningful dialogue about the future of space exploration. The path to Mars and beyond is a collective journey that calls for diverse perspectives and collaborative effort. Each of us has a role to play, whether it's supporting scientific endeavors, advocating for ethical exploration, investing in innovative technologies, or simply fostering curiosity in the next generation of pioneers. So, as we forge ahead, let us remain united in our quest to explore the stars. Let us embrace the challenges and celebrate the opportunities that come with reaching for Mars and beyond. The future of space exploration is a tapestry woven from our shared aspirations and dreams, a testament to what we can achieve when we dare to look beyond the horizon. In closing, we invite you to ponder your own stance on this monumental journey. How do you envision humanity's future among the stars? What stories will we write as we step onto new worlds? Join the conversation and become part of the narrative that is shaping the next era of human exploration. Thank you for joining us on this journey into the possibilities of terraforming technology. Together, let's continue to explore, innovate, and inspire for a future that extends far beyond the confines of our pale blue dot.